Hello YouTube viewers, welcome to my channel Science to Technology. In today's show, Science Thursday, we're gonna talk about Thorium Reactor. I cannot tell you how many times people have requested me to cover this. Well, first, before we go into basically thorium specific reactor, we have to understand nuclear fission, not fusion, fission. Now, fission is a form of what we classify as elemental transmutation. What does that mean? That simply means, let's say you take carbon and you oxygen. You get carbon dioxide, but you still have carbon and oxygen. In nuclear, that does not happen. Basically, matter gets destroyed. E equal to mc square applies. So basically, you can start with uranium, and at the end, you will not have uranium. It will not mix or bond with something else. It will physically disintegrate. And where does the energy comes from? That oomph in nuclear energy, that basically happens because when you add up, basically, you would think, right? Let's say the atomic mass unit of this puppy was, let's say, 200, and once you wanted to, basically calculate all the ejected parts, you will find something is missing. Let's say 200 was starting mass, the end mass would be, let's say, 198. What the hell happened to that 2? Now that 2 would be the part that went into E equal to mc square, and you got the energy of it. And that's why it's so powerful. On a molecular level, on a basically atomic level, it's turning that atom into basically energy. Now again, not complete of it. It's not like, oh, this whole atom went up, this whole atom went poof. That will only happen with antimatter reaction. But on a basically as close as we can get this puppy, this is very high energy event. Now how do we accomplish this thing? Basically converting matter into energy. Basically you take an atom which is almost at a breaking point. It's like it's too heavy, it's barely holding on. It's like, I cannot do this. The nucleus is like almost stressed to its breaking point, and then we basically take a neutron and collide with it. How do you get neutron? There are generally multiple options. Easiest one would be taking another radioactive material which has neutron particles emitting out of it, or gamma radiation. So you take neutron and boom. Now what happens here is very interesting and very critical, and it applies to almost all nuclear fission aspects. You take a big heavy element, you add neutron to it, it breaks it apart, because it's like it's almost at breaking point and you just broke it, and the output would always be two major particles and multiple neutrons. Now that multiple neutron is critical aspect, because let's say you put one neutron in and you got one neutron out, and you still got the energy output, but problem, it will not be a chain reaction, because that's it. That one neutron will only cause one reaction. That will cause one. That's not too much. And you have to understand, we are talking about molecular level stuff, so it's not too much energy. But in current scenario, what we have is like, instead of getting one neutron, we get 3 neutrons, or sometimes even more than that. Reality of that means, that guarantees that there will be another atom nearby it, and it will hit that and cause the same reaction. That's what we call chain reaction or runaway reaction. So once you have this, that gives you a throttle factor. Basically, if all three are colliding, your reactor is going up in the power. You're like, bro, it's going too much up in power. You're like, calm down. You add moderator. That's moderator is gonna affect on neutrons. It's like, bro, okay, calm down. Instead of all 3 getting married, only let 2 getting married. So that's how you control it. That's why that extra neutron is very critical. So this is fusion. Surface level, there are people who study this whole goddamn thing for like years before they can reach a point where they know, and now I understand. I'm not there yet. So this is fusion surface level. So what's the problem with this? Well, it works. It's a real thing. Problem is, when we break something heavy, we still end up with something heavy. The 2 particles that we get out are still not as light as basically helium or nitrogen. It's still heavy. Consequence of those are because they are still in a state where they are not stable enough, so they are basically acting as an equal to mc square battery. So instead of a reactor, you have a nuclear battery. What does that mean? That means it's dumping energy. How does it dump energy? Generally in a form of radioactivity. What does that mean? That means very, very high energy photons. It's radioactive, basically not good for life. So that is created. Now those elements, generally because of the amount of energy is dumping away, it generally goes down in lower energy state very quickly. Basically one element you will get, it dumps its energy, another element state dumps its energy, another energy. Now in the fission world, the amount of energy the lowest energy that we end up is still so goddamn high energy radioactive stuff that elements will be for hundreds of years ludicrously lethal to humans. Basically the containers that carries this puppy will be dangerous for human life for 100,000 years. Let that sink in. 100,000 years. Like Jesus is only 2,000 years ago. So this puppy goes far back. Basically, if we are starting to make this puppy today, basically, I don't even know how many generations forward, they're like, oh, in 1985 or somebody made this puppy, because it will still be radioactive. It's very dangerous, and throughout that whole time it's very radioactive because it's still dumping that energy. So E equal to a very high energy level. This puppy is dangerous, and because the photons are such a high energy level, it flat out destroys DNA. It's like it does not like heat up some molecules. It's like okay, higher vibration, that would be microwave. This puppy is like it just wrecks it through. So we have to contain it. That's not big enough issue, because we can contain the nuclear reactor, so that means we can contain this puppy. It's just that we have to store it, and store it for long term. That's why people have given up on nuclear fission basically. And that's the whole reason. Every time you see people are protesting and all that, just the protesting is not because of nuclear power plants or Chernobyl or Fukushima. It's generally because of this goddamn thing. It's like you are building something that we have no way of tackling, no way of handling, and we have to make sure that it's quote unquote safe for 100,000 years. Humans don't live that long where we can guarantee something like that. So that's why many people like, dude, we can't handle this, and let's make sure we do not create too much of it. So flat out many people like, nope, no nuclear power plant. That's the primary reason. Another aspect of that, let's say you took the power plants and you had any malfunction. We are humans, we make mistake. I'm not talking about malice, I'm not talking about somebody going tick boom. It's just malice, as in like, oops, I made this mistake, or something else happens. Or Japanese ego, like even though people like Nuclear Safety Commission is like, bro, or your seawall is not high enough, and all, why the heck all your backup generator is below ground where it can be flooded when you are next to a fault line where tsunamis happens. That's why I'm saying it's not malice, it's like a fallibility, human fallibility. Not only these power plants can go boom, that boom part is not big of an issue, because they are designed with a dirty fuel. They are not what we call enriched fuel. Enriched fuel is used in weapons. This puppy has to go on, it's like a slow burning candle. So they have very contaminated, basically 20% enriched. Benefit, very good throttleability. You can like easily calm, you increase the power, easily lower it down. Side effect of that means when it goes boom, basically when you scatter its material around the place, in case of a boom event, the boom will not be powerful, but the amount of material it will spew out, those material would be so radioactive, you'll be like, bro, it would have been better if you dropped a nuke here. It literally is that radioactive. That's the problem with this puppy. And because of the energy levels involved, because of the amount of contamination involved, this can contaminate the whole area. Basically, you are talking about a small area to a whole state can be contaminated by this puppy. And let's put cherry on top, it can be contaminated for a very long time, because I specified the radioactive byproducts can remain radioactive for very long time. So you can have one power plant accident and that could contaminate the area, and you're like, okay, that same happens with tsunami and something like that, so it's not too much of a big deal. But here, after tsunami, people return back. Sometimes next day they start to return back and start to figure out how they're gonna solve the situation. Here, yeah, come back after like 100 years. So that's the harmful reality. That's why people don't want to do it. It's not just like, oh, our designs are safe. Again, humans designed this, human tested this, human fallible. So that's why people are not that interested in fission anymore. Now, why so much hype around thorium? Well, thorium, the reason why Indians are so excited about this, because India has a plan known as India's 3-stage nuclear power program. Now, this program was created by Homi Jahangir Bhabha in 1950, basically just after independence. The reason for this is India has a uranium reserve, but it's not too big. It's basically we have to import uranium stuff and all that, yes. So we have uranium, not enough, not easily accessible. So they're like, dude, that's a weak point. Basically, if you want to run a country on nuclear power plant, you have to figure out how the heck you're gonna fuel it. You do not want to be like, hey, call up someone and it's like, can you give us a discount or something like that? So India has world's largest deposit of thorium. How big is it? Well, right now all the accounted for, basically we know this much thorium is on Earth. 25% of that is in India. To give a context of that, next closest does not even come this close. So it's like India got more than enough. And in terms of even worst case scenario, like let's say conversion efficiency and all that jazz, we still have more than enough energy in those puppies that is like, yeah, for thousands of years we don't have to think about it. It's like, we got this taken care of. So that's why it was so enticing. Like, okay, India has thorium and nuclear power plant does allow us to like get independence, and we don't have to worry about like, hey, China is dealing something hoo-ha with a river system, or somebody else is cutting something, like you don't have to worry about it. And here's the most amusing aspect of it, so that it has the same principle, like heavy element breaks into a smaller one. But here's the thing, the smaller ones, they are lightweight comparative to uranium, so those will be radioactive only for 300 years. Now 300 years is something human mind can understand. Like, I've been to temples that are older than that, I've been to homes that are older than that. So 300 years is like, I got this. Like at 300 point I can understand, like if you built a architecture, if you built a building to handle this contaminative stuff, it can withstand long enough. There is like, okay, after that, after the building crumbles apart, the stuff inside it will no longer be dangerous. So I can understand that. It's like 300 people like, okay, we got it. Now, because of the system efficiency, because it's a next generation system, you build it first or you build it better. This is build it better department. The system efficiency, the total round of efficiency means it produces less waste. So not only the waste is very short-lived compared to uranium puppy, this puppy is also pooping less. So instead of, let's say, per 100 megawatt you're getting 1 ton per year, this puppy would be per 100 megawatt 1 ton per 10 year. So you have less stuff to deal with. So that's ultra awesome. And it can't be used in weapon systems. Now, weapons are iffy subject. We humans like to blow each other up, and anybody who gets this technology wants to make sure that others don't get it. So there is a lot of conflict. Wars have erupted over there. So you have to understand that people don't want to invest in a technology, because again, even if the country does not go with war with you, but what happens if every other country is like, dude, I will put sanction on you? That will damage the economy very seriously. So people have to tread very lightly, so to say. So thorium gives us that advantage. Like, yeah, it can't be used at big boom devices, so it's very safe. That was the core reason why India is so focused on thorium. This was in 1950. Now it's so amazing. Let's come down to earth. Reality is, right now we do not know the cost. If you watch any YouTube video, they will like specifying thorium is cheap. Here's the technically that's impractical. That's like calling the ticket prices of Hyperloop. Nobody has built it. You cannot call it at this point in time. It's like calling, hey, there is a sand on the beach that has silicon, that means you know the price of a solar panel. That's not how that works. Fundamentally, we do not know, because there is no fuel architecture. Like, there have been labs, there have been systems which uses fusion to make energy, but none of them are working as a power plant, where it's like, okay, this is the mining facility, this is the processing facility, this is the transportation facility, this is how we actually convert it, this is we handle. Like, you have to calculate all of those, puppy, then you will have the fuel cost. We are not there yet. For lab, again, does not matter. For actual production system, we do not have the data. Another aspect, this design is inherently more complex. Nuclear power plants in simplest form can be built by a teenager. Yes, one teenager was close enough to actually doing it. So there is a nuclear power plant that are very simple, but this puppy is so goddamn complex. This is classified as breeder reactor. So you put another material there which is almost at the brink of becoming unstable. Then you put thorium, then you react with thorium. Thorium makes those puppy more reactive, and then voila, more fuel out of waste fuel. So awesome, design is awesome, but it's ludicrously complex on a chemical level. Like, if you try to understand the element path, it's like what? It's very complicated. Now, another aspect, it will be safe, because it will not have the Chernobyl or Fukushima, because it will use sodium. Now, you have to understand the problem with water is stable, but only at a certain temperature. Water is rocket fuel. It's basically hydrogen and oxygen. It's in a burn state. But what happens if you put that much energy, the amount of energy that was needed to put that in that state, you can break it apart. Basically, at that point in time, your nuclear reactor will literally have rocket fuel inside it. That happened in both plants, basically, so to say, Fukushima and Chernobyl. Is that when you have very high heat, you can break apart hydrogen and oxygen into hydrogen gas and oxygen gas. At that point in time, little bit of spark, boom, or sometimes just raw heat. And given the fact that you are dealing with nuclear reactor, you have more than enough heat. Thankfully, generally happens when there is a runaway and somebody forgot to put the catalyst. So somebody forgot to remove the catalyst, because if you have catalyst, then it's a runaway reaction happens. So people want to use sodium. Why sodium? Because water generally pushed to such a high level, it's very extreme temperature. It's like at 300 degrees Celsius, 400 degrees Celsius. And if you remember your school, you would know, wait a minute, shouldn't water supposed to turn to steam at 100 degrees Celsius? That happens, but there is a way to bypass that. Basically put it under pressure. Consequence of that, every pipe in your building is inherently running at the edge of its life. Basically, a normal pipe to handling that temperature and that amount of water flow would be like, let's say, this thick. But if you want to do that at 600 degrees Celsius or 400 degrees Celsius, your pipe thickness will go like this. Not to handle the temperature steel is like, bro, I got this. But the pressure, because it's a boom event, you have to maintain it. That's a very serious weak point. That's almost at the point of going boom. So people want to use sodium. Benefit: sodium is solid at room temperature and liquid at very high temperature. So it will go to the same temperature as liquid system, but it will not have the pressure. So steel pipes are like, I've got this, I'm calm, I can handle that. It does have a consequence of that is ludicrously corrosive. So, but it can be managed. People have figured out some new alloy compounds that can handle that, and mixing some things with sodium itself will also make it less reactive, but it can be done. Now, Reality is this puppy is still in research phase after 70 years of being found. Like 70 years, not 1 year, not 2 years, not 10 years, 70 years. The first design, the first architecture, all of that has happened long ago, as in 70 years long ago. It's very old system. At this point in time, India actually is building a system known as prototype fast breeder reactor. Awesome. The construction started in 2004, quite old, and the target was finish it by 2012. Now this is India, so we are like, okay, 2012 finished by 2014, 2016, 2018, 2020, still not finished. And right now the targeted point is first criticality event should happen at 2021. So reality is it's not a real thing. It's just like somebody did it in lab, somebody did the math calculation, and they're like, okay, this, I'm like, dude, you cannot tell the fuel prices because nobody knows it how to make it into a fuel. You cannot say it's more safer because that sodium safety can be used with any system. For example, NASA is building with stuff. They want to put nuclear reactor in space, so they built a system which uses sodium. His deal does not use thorium. They can still use the sodium system, and that's the only the way the government would have given them the clearance is like test it. What happens in a runaway event? What happens in a meltdown event? They did that. It was safe. That's what the whole point. Sodium can be added to any power plant. Like heck, you can take a normal, basically uranium power plant. It's like, bro, I want to remove water as a boom event. Okay, remove that. You can do that. Reality is that sodium makes stuff, that molten salt reactor. It can be done with any nuclear power plant. Is the basically what they are comparing is old uranium design versus new uranium design with a better fuel. It's like, yeah, you change two variables, not one. And uranium, every pipeline of it has been understood. It's like, okay, this company is manufacturing it, this company is mining it, this company is transporting it, this company is handling the waste aspect of it, this company is managing the containment units for that. Like every architecture that is needed to be in place, it's already in the place. And that's what the same basically conclusion came with Nuclear Commission of USA around 1960s. They were like, dude, we can do this, but reality is we know how to handle uranium. Every aspect of it has been taken care of. So instead of that, going into a new direction, and not to mention, we think it's safe. But what if happens if we actually start to run it as like, whoa, thorium has this kind of byproduct, which we have learned the hard way with uranium. Many people like, dude, I don't want to take that risk. Because again, many of these things could happen after 100 years. You're like, whoa, that reactor was doing that, and that's why it happened this, and it happens. It's a nuclear energy. It's not a laughing matter. So flat out, reality is not as the rosy as people think. And not to mention, India has spent like 5,000 crore. That's like hundreds of millions of dollars are poured into it, and it has been done. Like 70 years, like, and we still don't have any. Oh, this power plant is still not ready. So what we can expect in the future? Well, reality is we need clean and green tech. Global warming is here, global warming is real, global warming is getting serious. There's no denying that. However, that means we have a running clock. We cannot wait like fusion is gonna save us in 150 years. We will not have a comfortable enough life where we'll have enough money to deal with that situation. That would be like somebody giving you long life medication when you are almost buried. So flat out, we are running out of time. We have to react now. We have to take care now. Basically, our train is running downhill. We have to apply brakes now. Don't wait for like, okay, at the end of it, like once we are out of track, then we're gonna apply brakes. Like, dude, we are running out of time. Time is critical. So that's why I have become so jaded with the nuclear fission and fusion also. It's like, yeah, we're gonna happen someday. I'm pretty sure someday humans can figure it out, but it will be like, if it's 150 years from now, we will not have Mumbai and Calcutta to worry about at that point in time. So reality is time is critical. We cannot just like, okay, next 30 years. Don't have that time. And right now, at this point in time, if a country is like, bro, let's solve the energy problem, let's make sure our carbon neutral, can we do that? If we mix enough energy architectures, we can do that right now. Solar has already achieved what we call price parity, aka making electricity out of solar is profitable. People are doing it on their own. Government no longer even have to give subsidies, especially for very big ones. Very big ones are start to make profit very quickly. So reality is many people are doing it. Heck, India has crossed 20,000 megawatts of solar power. To give you a context, that's like 3 gorgeous dam, which is the single largest energy provider. India has a solar farm that competes against that. So reality is we have the solar, and you might be like, okay, what are you gonna do at night? Here's the deal: daytime is the most energy demanding time. If that time you can reduce all the carbon footprint, and you can tell all your coal power plants like, bro, come down, like go to idling state and turn off, go full power during evening time. Reality is you still saved like 4 to 6 hours of carbon dioxide emission in every coal power plant. That means a lot. Another aspect, India has a lot of hydropower. You can even do the same things like calm down during the day and night comes with the full force. We have also geothermal, little bit of geothermal, and we have a lot of wind also. Combined all of this, we can solve the problem today. And not to mention, we even solve the problem of how the heck you want to transmit the electricity, because AC transmission is not that efficient. So we have to use what we call high voltage DC. We have even figured that part out. That's the whole aim of European high voltage DC grid. So right now, if you want to solve Earth's problem, we no longer are in a position where like we have to wait for a magic technology like thorium or fusion and all that, or helium-3. God damn it, that technology is like bonkers. But reality is, we are at a position where if we start today, we can start solving today. It's not like, okay, 50 years from now. No, today you can start to make a difference today. And another aspect, energy storage is also maturing. At this point in time, you can flat out buy a lithium titanate battery system, which will be a bit more expensive, almost twice to three times the expensive of normal lithium ion system. But that puppy has a cycle life of 25,000 cycles. What does that mean? That simply means you have to replace it after 25 years. Basically, at the same time, you have to replace your solar panels. So right now, we are at a position, yes, it's a bit expensive, but it's reaching price parity, and more people are taking steps of it. But the amount of money we poured into fusion and fission and thorium and helium-3 hoo-ha, all of those are taking time away, and we do not have enough time. So, and you can still do fusion. Let's say we've taken care of all our power requirement by using solar, wind, hydro, and even clean coal and all that jazz. We did all of that, and then some engineer comes out like, this is how you make a reactor. Tada, no problem. Instead of that, we're just gonna substitute those. So time is the main critical aspect. That's why I'm no longer like so excited about like fusion, fission, aneutronic. That's why I'm really not looking forward to this tech. So this was my presentation on basically thorium power systems. Hopefully you liked it, learn from it. In that case, please click the like button, share it amongst your friends. That will help me a lot. If you didn't like it, didn't enjoy it, I urge you to press dislike, press it twice to show me extra disappointment, and please leave a comment because I try to reply to all of them. Subscribe, press the bell icon if you're free, and as always, thanks for watching.